Hi everyone, this is our presentation for the project of a computer vision course, which is about 3D camera calibration with geometry and 3D reconstruction. The subject of our scenario is a volleyball match in the Sambapolis gym. To analyze the match, we have access to 10 wide field cameras, strategically distributed to cover every aspect of the court. Our work is divided in 3 main parts. The first is camera calibration. This step is crucial because wide cameras introduce inherent distortion, like radial and tangential, that can affect distances and proportion, which are critical for accurate analysis. The second point is the creation of a multi-camera point mapping tool, where we aim to accurately project a point in all camera views. Finally, the last step is a 3D ball tracking system. These technologies could be very useful in a lot of fields, for example, sport analysis. For the state-of-the-art of camera calibration, there are 4 main methods. The first is self-calibration approach. This method doesn't rely on any external reference object, but it simply uses the scene itself to estimate the camera parameters. So, these have the pro to be fully automated, but as a disadvantage, it is computationally expensive and usually it has lower accuracy. The second is geometric-based method that is very effective in man-made environment, but struggle in a more general cases. The third is a deep learning-based technique that use deep models to find camera parameters. This approach is fully automatic, but is complex and needs resources. Finally, we have the chessboard method. This is one of the most used methods, and it requires placing a physical chessboard pattern in the scene. This method is very simple and accurate. For detection task, we find a lot of methods based on deep learning that use different architecture. We choose to adopt YOLO. That is a method where image is divided into a grid and predict bounding boxings and class probabilities for each cell of the grid. We find that YOLO is the approach with the best trade-off between speed and accuracy.
As Simone said previously, we divide our project in 3 main steps. The first one is the camera calibration. In order to calibrate our camera, we need to extract 2 sets of parameters, the intrinsic ones and the extrinsic ones. For the first set, we extrapolated using the Zank method, the chessboard method. For the second set, we required 4 paired points that we select manually using a tool we developed. With this set of points, we are able to determine the roto translation vector that represents the position of the camera in the 3D world coordinates. The second phase aimed to map 2 projected points belonging to 2 camera planes that correspond to the same 3D world coordinate. In order to do that, we use the homography matrix. It has an easy implementation and is very precise for the plane we select. The third step is a tracking step. We decide to reconstruct a 3D model of the field to show the trajectory of the ball in 3D world coordinates. We do it in 3 main steps. The first one is the detection part, using YOLO. For the second part, we triangulate the detection of different cameras to obtain 3D world coordinates, and then use particle filter to track the ball, with a prediction part and an update part based on the detection of YOLO. The final step is smoothing the trajectory, using univariate spline and moving average filter to obtain a very realistic trajectory. The final result of our project is an application where we select a source camera and a destination camera, and we could select a point in the first and see it projected in the second one. We always have a top view of the field below. The 3D tracking part produces a plot like this.